Hi, this video is about WebWork Homework 15 Problem 2. It's regarding isentropic efficiency for compressor. And I actually want to use this example to introduce a concept we actually didn't have recorded before. So now let's take a look at this example. It's adiabatic compressor. So we're going to draw a compressor. Start with 160 kilopascal and it's compressed to 1400 kilopascal. It tells me initially the air, so it's ideal gas, that comes into compressor at 300 Kelvin, and they tell us isentropic efficiency for this compressor is equal to 80%. Then want us to find out what is going to be required work, because compressor requires work come in, right? So we need to find this required work A and a unit of kilojoule per kilogram. So basically we do not know the mass flow rate. Okay, so how do we solve this problem? First, we're going to figure out what is isentropic efficiency. We talking about turbine isentropic efficiency before. That is, eta for turbine is what's going to be the amount of actual work generated over, if this is runs so perfect world that there's no friction, so it's going to be reversible work. So that, in other words, if it's isentropic process, that's how much work gonna generate it. That's our turbine isentropic efficiency. So knowing that, we can actually extrapolate it to figure out what is gonna be isentropic efficiency for compressor. So for compressor, that will be, okay, in actual required work, they ask us what's actual required work. So work required, it's actual, over, also it's going to be, if in perfect world, what's going to be required work come in. They both it's required work come in for isentropic process. Okay, so now let's think about it. If they're asking actual work required to come in, and in perfect world, if it's running isentropic, we know for compressor, we learned in the open system, compressor required work, let's do a quick recap. Required work is going to be equal to mass flow rate H2 minus H1, right? So knowing that, if it's in perfect world, we're going to have this M dot H2 if it's running isentropic. So I'm going to add S minus H1. Okay, and take a note, this is what we want to solve, and this is actually, I'm actually going to say it's not only that, it's this entire thing. Oops. What we're solving is actually this, right? This entire thing, because it's kilojoule per kilogram, and that's what we are solving. By the way, do we know this efficiency, isentropic efficiency? Yes, for mine is 80%, so that's known. So in order to find this whole actual work, we just needed to figure out H2S and H1, right? So now let's thinking about, there are a couple ways. They ask us if it's approximate analysis. So the first method, if it's approximate. If it's approximate, we're going to thinking about this H2S minus H1. That's going to be for ideal gas. To find entropy change, that's another topic. It's going to be Cp times T2 minus T1, and T2 is going to be, if it's in isentropic process, I'm going to add S, right? T1 is original temperature, that stays constant. It's this T2, that's going to be different if it's isentropic or if it's actual situation. Now let's thinking about CP. Here we approximate. Why? Because we assume we get what? The constant specific heat, constant CP. And our CP for air is 1.005. Then we just need to figure out T2S minus T1. And we do know T1. For T1 here, mine is 300 Kelvin. So minus 300 Kelvin. And I'm going to write down the unit for CP, which is kilojoule per kilogram per Kelvin. Okay. So knowing that, we just need to figure out T2S. So how do we find T2S? T2S, we know if is this going to be isentropic process because this is going to be ideal situation. If it's isentropic process, and you recall there are a couple of formulas we had before. The first one is T2 over T1 equal to V1 over V2 exponent of K, right? And another formula we have is T2 over T1 is going to be pressure ratio, P2 over P1, and exponents become K minus 1 over K. So those are two formulas you can use. And just a quick recall, those two formulas is based on approximate analysis, which means it's constant CP. That's how we derive this constant CP or constant CV. That's how we got those two equations. Now let's take a look. Which one would be better? We do know the pressure ratio, so it looks like this is a winner. Okay, so if it's constant entropy, so we're gonna have, using this formula, we do not know the T2S, so that's what we're solving. So T2S over T1, which is 300 Kelvin, that equal to P2 over P1. My P2 is 1400, P1 is 160. So 1400 over 160, that's our pressure ratio. And K, we said the K here. Oh, we didn't say. Okay, K is 1.4 for air. The specific ratio is 1.4. So it's 1.4 minus 1 over 1.4. Then you can figure out the T2. You can solve T2 for this problem. All right. So let's go ahead and solve that one. 1400 over 160. And then exponent, we're going to have 0.4 divided by 1.4. All right, then we're going to times 300 Kelvin. So my final temperature T2S is 557.528. That's going to be in unit of Kelvin. All right, so now we know that we can go back to this equation to find our rest, since you know T2 now, right? So let's go back to here. Then we say, I'm going to go back to say it's 1.005. Now we know T2S. If it's isentropic process, we're going to have 557.528 minus 300. That will give us H2, gonna give us this value. And that's what actually we needed to solve. Okay, so that's 1.005 times 257.528. That will give us the answer 258.816. Okay, so that will give us a unit of kilojoule per kilogram. All right, knowing that, we can come back to solve here, right? So now we can say our H2, what we are solving, this actual work for this compressor over mass flow rate, that's what we are solving in kilojoule per kilogram, is going to be our efficiency. My given efficiency is 80% times H2S minus H1, the entropy change if it's running isentropic. And then we're also using approximate analysis, assuming Cp is constant. And then we're also using the isentropic equation here for ideal gas. Now knowing that, so it's 80% times my value here, which is 258.816 kilojoule per kilogram. Then we have our answer for this problem times 0.8. I have 207.05 kilojoule per kilogram. Okay, so that's the first method, assuming it is isentropic process. Now we're going to look at method number 2. We're going to assume this, we're going to work on exact analysis. This is something I will introduce a new concept here. So previously we had equation for solving for exact analysis to solve our delta S entropy change. We have entropy change for ideal gas. We have delta S equal to S2 naught minus S1 naught minus R natural log P2 over P1, right? And where do we get S2 naught and S1 naught? It's going to be from the ideal gas table. All right, we introduced that, but we didn't use this equation to come up for isentropic. So this is where we are going now. If it is isentropic, which means our delta S is going to be equal to 0. So knowing that, we'll have S2 naught minus 1 naught minus R natural log P2 over P1. That's equal to 0, right? And that's the exact analysis. And then we're going to introduce another concept. Because this is, if we do our math first, is we will have S2 naught minus S1 divided by R equal to natural log P2 over P1. Then your P2 times P1 over P1 is going to be exponent, right? And R S2 naught minus S1 naught is starting getting a little bit confusing maybe. But what's this going to be when you have that? You can use in the math. It's basically exponent of S2 naught over R exponent S1 naught over R. All those actually also in your textbook, so you can look at it. So here, this is something they put into the table. They said all of that, we're gonna say this is gonna be equal to PR2, and this is gonna be equal to PR1. And what's this R here mean? That means it's relative pressure. So there's a table for that. That's going to be in table A17 for air. And A17 and beyond, that's going to be for other ideal gas. So knowing that, you have this very simple equation. That's all we need to know. It's what? P2 over P1. And we're going to write a subscript because this is a isentropic process. It's constant S. That's going to be P2 over P1 is going to be equal to PR2, this relative pressure, over PR1. Isn't that easy? Right? So that is the new concept I want to introduce. That is exact analysis for isentropic ideal gas. So that's another equation you could use. That's going to be a good supplementary to those two equations you had before. That's approximate, and here it's going to be your exact analysis. So using ideal gas equation, you could even come up with another one. So this comes V2 over V1. And if this is running as isentropic process, that's going to be equal to VR2 over VR1. Okay. Again, it's the same. So knowing this concept, we can come back to solve this problem. And go back to our logic here. We want to solve the required work right here per mass flow rate. And we know the efficiency is 80%. We just need to figure out H2S minus H1. And you have to be exact process. So first of all, can we solve H1? Is that exact value? H1, it's ideal gas, and they give us a temperature, so we can go use the ideal gas table to find our H1. That's our first step. H1 at 300 Kelvin. You might not have 300 Kelvin. You might have a different value. So now I actually have a table ready. You're going to go to table A17. And at 300 Kelvin, I have right here, do we have an H1 value? 300.19. 300.19. That's going to be kilojoule per kilogram. If you have some odd value, like for example 300, let's say 307, in that situation, you might have to do linear interpolation to find the exact value for this. Okay. And now let's go back. We need to go ahead and find H2S. We know H1 because we know temperature is 300 Kelvin. In order to find for isentropic H2 exact, so we need to, before that, we need to really go ahead and find out the temperature, T2S, right? How do we do that? We're gonna use this right here. So which of those two should we use? Yeah, we're going to use the top one. Why? Because we know the pressure ratio. So I'm going to write it down here. P2 over P1. And I can also write down, instead of in the subscript, I said if this is isentropic for ideal gas, P2 over P1 is going to be equal to PR2 over PR1. And now what's our P2 over P1 ratio? P2 is 1400 and P1 is 300. I'm sorry, not 300. It's 160. So it's 1400 over 160. 1400 over 160. And our PR1, we need to find the PR2. And can we figure out this PR1? That's going to be our next detective work. How do we find the PR1? So we said this is from where? From ideal gas table. Let's go to A17. So A17, PR1 is corresponding to temperature is at state 1, it's 300 Kelvin. That's where we find our H1. So let's go to the same table. At 300 Kelvin, you notice this another column right here, PR. That's our relative pressure. It's 1.3860. 1.3860. And the unit for that one is in, well, nothing, because it's going to be a unitness, okay? PR, it's not, even though they call relative pressure, but it's unitness. Remember, this is a definition of PR. It's exponent of something. That's going to be no unit. So knowing that, we actually just need to find a PR2. So I'm going to put into the calculator. So I have 1400 over 160, and then going to times 1.386. And that's going to give me PR2 as 12.1275. That's the relative pressure. Relative pressure, PR2. How would that finding this relative pressure help us? We can actually reverse back. We can go to the same table. We're going to go to the table A17 again. So now let's take a look at table A17. If we can find, so our logic is from PR2, we want to find what? The temperature. Or maybe we don't even want to find temperature. We want to find what? Our goal is, actually we want to find this H2S, because that's what we needed to find out, right? We need to find H2 for this isentropic. We are doing the whole thing in isentropic process. So PR2 is 12.1275. So let's go over there. Go to the table. Okay, so we're looking at this table. It's 12.125, so 1275. So it's going to be in between those two rows. And what we really needed to find out is our S value. Right? However, oh no, not S value. It's going to be our H value. So it's going to be using those two numbers right here. We want to find out our H value. So I'm going to write it down. Of those, I'm going to borrow those two. So I'm going to say I'm going to extract those two information out. So this is going to be our H column. This is going to be our PR value. Our PR value, if it's 11.86, our H value is 555.74. And if we have 565.17, that's corresponding to 12.66. And what is, so now we're done with that table. We have the value of our PR is 12.1275. So here we need to figure out, using linear interpolation, what's going to be our H value here, right? So go ahead and set up our linear interpolation. So I'm using 12.66. Actually, the other way. 565.17 minus 555.74. So we're doing delta H over PR, delta PR. Then that's going to be 12.66 minus 11.86. That's going to be equal to our delta H here. I'm using 565.17 minus this H2 you're solving, and corresponding PR value is those two. All right. So then we can find our H2. All right. Let's go ahead and put in the calculator. 565.17 minus 555.74. Then divided by 12.66 minus 11.86. And then we're going to times this 12.66 minus 12.1275. Okay, that's our value. And then I'm going to add a negative sign in front of that. Then plus 565.17. And this is what I have, 558.893. Okay. So now let's look at this number. Does it make sense? Yeah, I think it pretty much makes sense. It's in between those two values. All right. So that's going to be giving our H2 in kilojoule per kilogram. So what have we done so far? Let's just wrap it up with this new concept here. So we said if it's exact analysis for isentropic process, we have this two formula. So if it is isentropic process, we can use this pressure ratio. And since we know this pressure ratio is 1400 over 160, and then we can find our PR1 because we know the temperature, 300 Kelvin, we find our PR1 in ideal gas table. Then we solve this PR2 using this exact analysis for isentropic process. So knowing that PR2, we can go back to look at the same table to find our H value. And that H value is gonna be our H value for, well, isentropic process, because you are doing it, you are using this formula here, assume it's isentropic process. So that's your H2S. So knowing that, we can go back to our way beginning to look at this equation here. You know H2S now. So I'm going to go back to write it down. The last step. We know the efficiency, isentropic efficiency is 80%. And that efficiency is equal to this actual work, right? Actual work. And over if it's running isentropic, so that's going to be our H2S minus H1. And what we are solving is this value, is this right here. So we go ahead and write down our actual work over mass flow rate. That's going to be equal to our efficiency, 80%, over if it's running like isentropic. So 80%, our H2S is 558.893, just finding in the previous step. And our H1 is also actual reading from your table, 300 Kelvin, through ideal gas table, that's 300.19. 300.19. And they give us the unit of kilojoule per kilogram. So knowing that, let's go ahead and put in the calculator, 300.19, and then times our 80%. I have a value of 206.96 kilojoule per kilogram. And that is another answer come up with exact analysis. Let's compare these two values. Okay, previously we have 207 here. Wow, it's pretty close. This is there too. All right, so that's wrap up this example. It's actually quite good example, and it helped us to look into this exact analysis. I didn't do it before. I thought you don't need to know, but looks like WebWorks requires you to have that information, and it's actually good information. I should have put it on the video before. Now you have it. So hopefully this will help you at this problem. Okay, I'll see you at the next time. Bye.